Good afternoon, gentlemen. I am seeing that you guys only have 5 of you are there yet. And I know there will be some missing folks today. So I'm going to be recording this. And, where am I talking? Let's see, my headset. Where's my headset? Okay, very good. If you can hear me, that's always good. And of course, you're missing my face. Oops. I don't know what's happening. Share video. Okay. I had an important email from Wolfram. So let me take a look at this. Okay, so they are resisting the idea, but won't worry about that right now. Where did they go? Where did you guys go? Huh, it was here. Okay, we got the majority. I think you're seeing me and also hearing me right now. Very good. What we're going to do today, we're going to continue this idea of using optimization to eliminate those manual iterations in finding the best possible design out of multiple landers that may be optioned. You've seen the need for this with the solution of the test problem that you actually needed to search through a number of M's and N's for one specific laminate type. But of course, if you start using the optimization algorithms, this will generalize to much more options for you to try different laminates, and not only 0 plus minus 60s, but other ply orientation angles as well. And the problem with that is this is not a traditional optimization anymore. It will bring either enumerating the options, creating tables, or going into programming approaches, among which is one of them called branch and bound algorithm for integer linear programs. And this is what we are going to be doing in this particular lecture. Now, branch and bound algorithm is an algorithm that you just need to know its name. You don't need to learn how the optimization works, but it's such a simple notion that actually you might find it useful at some point in your career that you should know at least the outline of what the branch and bound algorithm does. Have to decline the call. And it has something to do with linear programming. Branch and bound is an implementation using linear programming to solve some integer programming problems. And then we're going to actually demonstrate that it is integer linear programming. that will directly apply to perhaps the problem that you worked on or something different. You'll see as we go along. Let me briefly go over what we covered so far. We said this is used as an optimization, and the standard form is one objective function. It could be weight, it could be number of layers that you minimize that will directly translate to weight. And this is typically, in your case, there were two variables. Small n was 2 in the test problem. So there was x1 and x2, or m and n. And that gives us the number of layers that we could try to minimize. And then we have constraints in some functional form that says inequalities, GJs. In this case, these will become some stiffness properties that we may want to put limits on. There are typically equality constraints in optimization, but we may or we may not need this. You will see as we go along, perhaps we'll utilize the use of equality constraints as well. And the design variables in the most general case are real numbers that will change between some lower limit and upper limit, not integers like 1, 2, 3, 4, 5, as was the case in your test problem. Then we did go over some of the different versions, and we jumped into what if you use traditional optimization for composite laminate, and you could have a different orientation angle, and you can assign different thicknesses to each, but without these T1, T2, and T3 being integer numbers, you're not going to get much mileage out of it. But if this is the only that you have, you will implement T1, T2, T3 as continuous optimum solution, and then you round it to nearest integer value, which may or may not give you the optimum. And on top of that, even the rounding off to the nearest integer value might be very time consuming. In case of 3, that was this case, it's zeros and 45s and 90s. Then we said, okay, we might be able to formulate some in-plane stiffness design as integer linear program. But let's start with some definition of the quantities that we're going to look at. These are in-plane stiffness properties, A11, A12, A22, A6. This is the A matrix that we're going to be optimizing. Okay. Now, ply orientations are there in this V1 star and V3 star. This is the case where you might assume the laminate to be symmetric, because if it's not symmetric laminate, you play symmetric, there may be other terms. And then you can also assume balanced laminate. For a balanced symmetric laminate, we said V1 and V3 are given in this particular form. These are equations that I've got from earlier lectures. But I think this is where we left off last time, that we're going to be actually trying to optimize with in-plane stiffness, either objectives or constraints. So we're going to either require, say, A66 to be maximized, or A1 to be maximized or minimized. So every one of those options for these A's are possible, and the design variables go into V1 star and V3 star for fiber orientation angles, and the total thickness is in here. Total thickness will change also with some of these variables, but that is also pretty simple to compute. V1 star is if you take the distinct fiber orientation angles. Like in your test case, theta 1 was, say, plus minus 60, and theta 2 was 0. And you don't have theta 3 and anything else after. But if you have more ply orientation angles in play, then this can be extended as a small v1, small v2, small v3, however many distinct orientations that you have, and only half of it is in the optimization. The total laminate thickness that corresponds to n total layers is dictated by how many layers of distinct orientations that you have. And we define these small vi's to be a percentage of that particular orientation angle, ti, divided by the total thickness. So how much of the laminate total thickness h is occupied by, say, 0-degree angles, which will give you vi number for that particular orientation. Let's say I equals 1. If I is equal to 2 is the 0-degree angles, or 6 plus minus 6-degree angles, then this will give you the total amount of plus minus 60s in the laminate compared to the total thickness. So these will also change. They're strictly equations that we have seen before. Now we're going to try to actually start putting them into some mathematical formulation. And in there, I'm going to pick, for example, 3 different orientation angles. With theta P, theta Q, theta R. Now, of course, PQR instead of PQR, I can use another subscript to represent them. Say, for example, instead of P, if I put Z, theta of Z, I may call that to be the 0-degree orientation angle. And theta Q might be plus minus 45. Theta R could be plus 9-degree plus. With each ply being thickness T, in which case, for the case of n equals 3, V1 star is 2T over H, number of 0-degree orientation angles, for example, or 45s, or whatever you choose those P's and Q's to be, and each of those can be computed like that. If you have, let's say, you're building a laminate that is composed of zeros, plus minus 15s, plus minus 30s, plus minus 60s, plus minus 75s, and 90-degree plies, then you're going to increase this to be a longer list. That will still give you V1 star and V3 star, knowing the number of layers of that particular orientation angle. So specializing this to, let's say, only 0s, 45s, and 90s, V1 star will then, putting those, let's say, P represents the zeros, and I put NO in here. I don't know why I use O. I could have used the Z for this. And then if you put 0, cosine 0 is equal to 1, this term becomes 1. That's equals NP or NO. For times 45, this will be 2 times 45, 90. That will disappear. So this will become 0. There's no NQ or N45, which I represent by NF. And for 90-degree orientation, I use NN instead of NR. So this is the number of 90-degree plies. And 2 times 90 here, 180. This again gives you minus 1. That's why in V1 star, this is NO minus NN. So V1 star will simply be a function of the number of 0-degree plies and number of 9-degree plies here. Multiplied by 2T divided by total H, which you can actually write total H in terms of the individual ply counts, which is then total H 2 times thickness. This is from the symmetry. You're always twice taking the twice of the top half, and and number of zeros plus 2 times the number of 45s, because we are counting and f equals 1 means there is a plus 45 and a minus 45. So it will always come as a pair of plus minus 45. So for example, if you were adapting to your formulation with only 2 angles, 60s and zeros, you may have represented this with NO and NS for 60. Lack of any better representation. There wouldn't be any NN, so total thickness will be 2 times T times number of zeros plus number of plus minus 60s. And V1 star would only be in terms of 2T divided by H and O, and V3, the NN will disappear, and this will become NS, number of 60s, in the test problem that you solved. So right after this, you can actually try as homework. I think this may be a good homework assignment. I will do this as an assignment to do the, well, no, we cannot do your test problem because that's nonlinear because of the Sahel constraints. So we can basically find the A's in terms of number of ply counts. So the variables NO, NN, and NF for this case of 0s, 45s, and 90s here are the ply counts of that particular orientation angle. And remember, NF for 45 will always multiply it by 2 because we're going to assume every plus orientation of 45 will come with the minus orientation together. So that balance condition will always be satisfied. Any questions so far? Okay, the last message here there says we lost audio. I think you do have audio now. And if I hear yes, we do, then I'm going to continue. Thank you, Edison. All right. And no question from Edison. Excellent. So what do we do? What can we do with this? Next chart, I'm going to put all of those together. Now I've expanded the U's and the coefficients, the in-plane stiffness coefficients, A11, A22, A12, and A66 is now 2 times T multiplied by this constant. This is a material constant for a given material. This U1, U2, U3, and everything else is constant. And it has a number of 0-degree plies here, number of 45s here, and number of 90s. So the ply count variables for distinct orientation angles, if you look at A11, A11 is linear in terms of NO, NF, and NN. So as every other stiffness term. They're all linear in terms of the ply counts for the in-plane stiffness. There's no bending stiffness in this particular formulation. The bending is going to be more complicated because what we are assuming for the in-plane is their relative location. It doesn't matter. So for optimization formulation, I can always consider all of them the same orientation angles as lumped together into one block that is represented by this N0 or NF or NN, or if you're using any other alphabet for your stacking sequence, that particular alphabet, whether it has only plus minus 30s or zeros and 90s, so that alphabet is going to change depending on which orientations you want to keep in the stacking sequence formulation. Now, out of these, I can also look at some of the engineering constants. Yes, A's are constant, but there's E, modulus E is constant or linear in terms of NNs and NFs and so on and so forth. It's not. But GXY is, because GXY is a function of A66 only, and A66 is linear in terms of ply counts from this equation. And it appears that I have to multiply this G with, or divide A66 by H, but thickness and H are related to one another. So if I write this like this, all I have to do here, put in instead of H, put this equation for H, which is this one. Okay? And that becomes also a linear in terms of N0 and Nf. So some of these quantities like nu also. Nu is defined as A12 over A22. This is actually a linear expression again in terms of A's. So A12 over A22 will be this, but if I write it as equality like this is an equality expression. So I can put a constraint on the nu xy to make the linear constraint out of it. There's actually a nice way of seeing what engineering properties are linear in terms of V13 and V1 star and V3 star. And that's from the Mickey's diagram. If you look at the Mickey's diagram, you can actually plot G in that diagram. And let me put it into presentation form and give you a graphics of it. Okay, pen color, let's make it black. So our diagram V1 star and V3 star for in-plane lamination parameters was something like this. And this is not out of scale, but this was all 0-degree layups. This was all 9-degree layups. This was all 45-degree layup. And the GXY contours in this diagram will be horizontal lines because GXY is only a function of V1 star or V2 star. I forgot which axis I plot where, so I need to check that. But the constant shear modulus lines are horizontal lines, and plus minus 60, plus minus 45 for a given layer will give you the largest shear modulus. If you look at the Poisson's ratio curves, they'll again be lines, but there will be some angle. So they'll also be nu xy lines will be also linear. EX of a laminate is not linear. Effective modulus EX or EY effective is not linear in terms of V13 and V3 star, and you'll see some curves that will go like this in here for their values. But A11, A22, A16, and A66 are actually linear if you plot in this diagram. EX, of course, is a complicated expression. It has A1 square minus A11 times A22 divided by A22 square or something like that. So this is not linear, and this is not linear in terms of the lamination parameters V1 star and V3 star. So how do we solve this problem? It's a linear programming problem. Linear programming problems are simple to solve. Every software that you can have as an engineering software will have linear programming solution. MATLAB, Mathematica, Excel, they will be able to solve linear programming problems very easily. But if you say, I want these numbers, integers, then the optimization solution is not simple anymore. But for linear programming, there is an algorithm which we call branch and bound, which is rather simple to implement. It's a very, very logical algorithm. You first solve your problem as a continuous problem, continuous linear programming problem, and find the value of an O, an F, an N, or whatever alphabet that you're using. And that may give you some non-integer values. Okay? The trick is then to go into the design space and branch the design space by excluding the non-integer solution by putting bounds on it. And what I mean by that is this. Let's say that I'm trying to design a 16-ply balanced symmetric laminate with these 90s. So, and O in here is showing the number of 0-degree plies, and F is showing the number of 45 plies in pair. So NF equals 1 means there are two 45 is 1 plus and 1 negative. And N will count the number of zeros, individual single 0-degree plies. And I chose a material that has material constants given here. It's not changing as a part of the design problem. And I'm requiring to maximize A11 such that GXY, engineering constant, is larger than 12 gigapascals, and A22 greater than 20 meganewtons per meter. Okay. And the ply thickness is 0.125 millimeters. So what I'm trying to maximize in this case is A11. And A11 ideally is a function of all three ply counts, 0s, 45s, and 90s. And if I put these U values into their places, I find A11 divided by 10 to the 6 to be in this form. Okay, this is what I'm trying to maximize. And then G1 says must be larger than 12 gigapascals. So G1 expression is 12 times 10 to the 9 times H minus A66 divided by 10 to the 6 must be less than equal to this expression must be less than equal to 0. I took the 12 on one side and I made this is the constraint, and I need to show the constraints as G1 must be shown as less than equal to 0. Okay, and the constraint is this one. So 12 minus GXY, which is this expression, must be less than equal to 0. This gives you the inequality constraint in this form that says, hey, 2.425 times number of 0-degree plies, minus 3.8 times number of 45-degree plies, plus 2.45 times number of 90-degree plies must be less than or equal to 0. Ends are not integers in this case. I'm leaving them to be any value. The G2 constraint in this case is this, that A22 must be larger than 20. So I need to write G2 to be less than or equal to 0. Therefore, I take A22 and put it on the other side. So 20 minus or minus 20 times this. I mean, you just need to do that expression. This is the constraint. And if you write it in terms of use, this as the constraint. So this is the objective function. This is G1, and this is G2. G3 is a constraint that says design a 16-ply laminate. I'm not trying to minimize or maximize the limit. I'm saying I have to have a 16-ply laminate, meaning that I have a constraint. And this is actually not G3. This is equality constraint, H. H1 equals 0. And this is the constraint. I should have represented this as H1. That says number of zeros plus 2 times number of 45s plus number of 90s must be equal to 8. Now I have one more constraint, and that is the number of plies cannot be less than 0. And I also have this 16-ply, so the maximum number of zeros can be at most 8, because there is no, if there is no 90 and 45, this is the maximum number of plies that I can have. I cannot have anything more than 8. So I put a bound on number of zeros that must be between 0 and 8. Number of 45s can be at most 4, in which case number of zeros will go to 0, number of 90s will go to 0. So this is the bound for the number of 45s, and this is the bound for number of 90s. These are the bounds. Okay. Now, this is a linear programming problem that any software that has any decent engineering software will solve as a linear program. And it does. I'm going to show it later on. That when I solve this problem as a linear programming problem, not integer programming problem, as a linear programming problem, I get a solution that says the A11 that you can get is 94. And the number of zeros is, you need 3.51 plies of zeros and a pair of 2.24 45s and no 90s. That will give you a maximum of A11 equals 94. Now what I do at that point is I branch my design space into 2. I say, I look at this, and this is the further the number further away from an integer solution. So which design variable that I branch depends on how far a particular value is away from its integer value. The nearest integer values to zeros is either 4 layers of zeros or 3. Okay, and you 0.5 away almost from each of those, 4 and 3. This, on the other hand, the solution that comes closest to this is upper value of 3 and lower value of 2. But this solution is closer to 2. So the first branching that I do is the one that's further away from the integer value. And when I do that branching, I say, okay, do not let NO to be less than 4. That's one branch. This says, okay, N must be larger than 4. So I eliminate 3.5 fund to becoming a solution by doing so. The other branch says, hey, the nearest lower integer is 3, so NO can be between 0 and 3. So basically, the original constraint was NO must be greater than 0, but must be smaller than 8. I'm replacing this constraint by 2 constraints. One on this side, I don't want it to go NO to go to 3.51. By doing so, if I make a plot of the design space, let's say I'm looking at this design space and this is an O and this is an F, and the solution that I had was here, I'm basically saying you cannot be on this side of the NO, you cannot be on this side on NO. And I solved this problem twice, one with this constraint, one with this constraint, and see what other result I get. So that's what the second linear programming and third linear programming does. This solves the problem again. Oh, come on, don't jump. This branch solves the problem again when I force NO to be less than 3, and this forces them to be greater than 4. Okay? So when I do that, in one branch, I get no solution. On the other branch, I get a solution that says NO must be 3, and NF comes out to be 2.5. Now here, NF was 2.24. Still not integer, but NO is now integer. Okay? So, and then my maximum value is now 87.22. And then I take this, because this is non-integer solution, and I actually create 2 more branch by replacing the constraint that an F must be this, okay? And I'm getting 2.5. When one branch says you cannot be less than 3, and the other branch says you cannot be greater than 2. So those 2 branches are these constraints. These 2 constraints are now replacing this. And I solve it again. And I get NO equals 2, NF equals 3, and N90 equals 0. And this is an integer solution. So basically, I solved the integer linear programming problem, and this gives me no solution. This is what the integer linear programming does. In the tutorial, we're going to actually do this, implement this as like the poor man's integer solution. And then I'm going to use Mathematica again to actually solve directly the integer linear programming problem. Because Mathematica have an option to solve integer linear programming. Okay. Let me see. So this is what we're going to do, and you're going to see this in action. Then the next thing is, although we're not going to be doing the binary programming yet, sometimes integer solutions, integer programming is not good to solve stacking sequence optimization problem. Sometimes we're going to actually prefer a variable that will be only 0 and 1. In which case, I need to use design variables that are binary numbers, zeros and ones. Now, to emulate that, if your programming algorithm does not have binary programming, then you need to convert your problem into by doing change of design variables. So for every integer variable, I create an equation that gives me a version of that number, where these x01, x02 are all binary numbers, zeros or ones. Okay, this is either 0 or 1. This is either 0 or 1. And x03 is 0 or 1. If I have these variables 0 and 1 here, 0 and 1 here, 0 and 1 here, 0 and 1 here, I can get all the numbers and O that is between 0 and 8. There is one caveat to this, that x01 plus x02 plus x03 plus x04 must be equal to 1. Because if I have, I can have actually all of these to be 1 moment. No, forget what I just said. So if this is 0, if this is 0, if this is 0, if this is 1, I get 8. If this is 1, if this is 0, this is 0, this is 0, I get 1. If all of them are ones, 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 and ones, I get an O to be actually larger than 1. Larger than 8. I get 4 plus 8 plus 4 plus 2 plus 1. So that gives you an O to be much larger than 8. Whether you have that particular constraint in your problem, in the previous problem you had that constraint. But in general, you don't really have that. The only $105, you need to add additional binary variables into this list. That will give you any integer number between 0 and 150, depending on the values of the x01, x02. So every integer variable is represented by multiple number of binary variables. If I want x and O to be largest 8, then I have to really add that plus that plus that plus x04 must be equal to 1. If these are only 0, 1 variables, what is the meaning of this constraint? Want to give it a try? Want to answer this question? What is the meaning of that constraint that I just put in there? Waiting for an answer. Oh, I lost all the markings. Where are my markings? I lost all the markings. Anyway, the meaning of that constraint is only one of them can be 1. If any one of them is 1, the others must be equal to 0. And you're going to find this actually to be a very useful construction for stacking sequence optimization, where we will actually put through the thickness a binary number to show whether a given ply is 0 or a 45 or a 90. It can be any one of them, but it cannot be half and half. Okay, so you're going to see this actually implemented in the tutorial. So with this was the last chart anyways, that we will put this as an additional constraint that that minus NO must be equal to 0. And in that case, we can even relax NO, NF, and N to be integers, because if these are binary, x0 through x4, you'll get NO to be an integer number anyways at the end. You can either replace that you see NO with these, or add this as a constraint and solve the optimization problem. I know for those of you who have not seen optimization, this some of these things have become somewhat confusing. But this is the, I think, minimum, something minimum about how you use optimization in design formulation, even though you have not seen the algorithms in action, although with the poor man's version of branch and bound. You could have done all of this without even seeing how branch and bound is handling the integer linear program based on just availability of a linear programming problem package, linear programming package. So with that, I'm going to go to the tutorial, and I want you to ask questions when it's something that doesn't make sense for you. Do ask questions, otherwise, how am I going to know if I can explain something better or not? Otherwise, I'll keep assuming that I'm such a good instructor that whatever I say is completely clear and I'm the best teacher in the world. Don't do this to me. Ask questions. Because I'm not the best teacher in the world. I can only try. One can always only try. There's no such a thing as anybody being the best in one particular thing, or there's always somebody else out there who'll be better than what we are. Always go with that idea, and you will not go wrong, because then you will be always striving to become the best. So learning never stops. You always learn. Right? Right, guys? Come on, say, all of you, say yes. Okay, 1 yes. 2, 3, coming. All of them are coming. Yes. Come on, don't be lazy. Type yes. Oh, no. 4 out of 8. not bad. All right, let's go to the tutorial. And as I said, please do stop me and ask a question. Otherwise, I'm going to start feeling that I'm the best in the world. All right, let me open my CLT version 3. All right, and execute my old CLT code. So now I can check if this exists. Yes, it does exist. So all these things are available for me. So first thing that we're going to do is we're going to look at linear programming in Mathematica. And first we're going to look at built-in Mathematica linear programming. As I said, if you are a MATLAB user, there should be a linear programming in Mathematica that you can use. If you are an Excel user, I think there's linear programming in MATLAB. But for this particular case, I am going to use Mathematica. And Mathematica originally had this linear programming as a separate entity. It still does. So if you type question mark linear programming, you will see what it does. If you want to know what other functions that you have with the words star, linear, star, this is going to search Mathematica library, and star is a wild character. So anything that is in the middle or in the beginning or at the end, linear, will come. And these are all Mathematica functions that has the word linear in it. So you can see like Kalman linearize, dual linear programming. Oh, gee, this is new. I did not know that this existed. Dual linear programming is very useful for optimization purposes, but it's a deep topic that we're not going to go into it. Find linear recurrence, generalized linear model fit, linear filter, linear fractional optimization. Aha, this also I didn't know it existed. Well, these are all for me to look at afterwards. This is one thing about Mathematica. I think they make improvements. And the email that I sent to Wolfram, that I just got a response, I asked them why binary was not used, and they're saying use Boolean instead of binary, which you can, but that wasn't the point. Linear model fits, linear optimization, linear programming, linear solve, log linear plot, all kinds of other things. Just for curiosity, I'm going to look at the dual linear programming. Linear programming, it exists, but they're not showing how it's used. Internally, they use it. That is sneaky. What am I going to do if I don't know how to call it? Linear fractional optimization. This has information on it. Linear constraints constants. Okay. This is interesting. I don't know what the use of this is, but don't worry about it. Right now, we're interested in linear programming, which is, where is it? Linear programming? Here, this one. Linear optimization also exists, and it shows you actually, it's not going to be different than linear programming, but it's the same thing, constraints and variables, whereas linear programming only works with matrices like this. So we'll come to this in a minute. There's also more general minimization and maximization in Mathematica. This is one of my favorites. It's either find minimum or find maximum. And if you look at this, find minimum and find maximum, is actually very close to this. But this solves nonlinear problems as well. And it solves also linear problems. So basically what this is, linear optimization, is a version of this, which is, this is more general. But if you define your functions linear, Mathematica is actually internally capable of finding what function is linear, what function is nonlinear, and picks the algorithm internally. But if you know it from the get-go, you might actually want to use this. So this is something that I didn't know that it existed. I think I may actually convert my tutorial into linear optimization, because this define function, you define constraints, you define variables. It's a linear objective function f, subjected to linear constraints, counts, and then this you just give the matrix coefficients of matrices without giving the function itself. And you can also do domain descriptions in there. So don't worry about it too much. But if you want to play with them, I think there's a wealth of information that you can play in here. So these are some of the functions that we're going to be using in the following. That's why I want to show you these. Anytime you need more help on those, you can go here, you can go local, and a new window will pop up. And it will show you how to use find minimum with all their options and some details of the options in here. Okay. And some examples in here. How to find my minimum of x times cosine x, for example, when x goes from 0 to 14. So it's a tutorial on how to use find minimum. But let's close that. Let's go to our problem in plane stiffness design. So I take those equations from my charts that I'm defining an in-plane problem with V1 star and V3 star. This is still general. I don't have a laminate alphabet at this point. But I know that A11 is equal to H times U1 plus U2 V1 star plus U3 V3 star, A2 816 and A66. These are all definitions from my charts that I basically put in here. This is a graphics that I pasted in here. This is not a input or output. This is just text itself altogether in this one cell. So I have A11 through A66 defined in terms of U's and V3 stars. If you are going to be using an alphabet, depending on which orientation angles you want in your laminate, you're going to define these number of layers with those alphabets. And in this case, I'm going to make a laminate with zeros, plus, minus, 45s, and 90s. And I use NZ and N and NF to represent those ply counts. NZ is the number of 0-degree plies, and 90-degree plies. NF is plus minus 45 plies. And note that NF equals 1 means there are two layers. One is a plus 45, the other one is a minus 45. So if I put this alphabet into this equation, I get this expression. And this is something that if you have a different alphabet, you actually need to type this equation with your proper ply count. So for example, if you build a alphabet with 15s and 30s and 45s and 60s and 75s and 90s, you'll introduce another variable for each of the distinct orientation angles, a new variable, and you will put that in here, okay, and in here. So if your homework is do your test-like problem with you only have zeros and plus minus 60s, then NZ will represent number of zeros, and you can get rid of NN, and you change NF to NS for 60, and you have the right V1 star and V3 star. So your alphabet is going to directly influence this. In fact, let me put that as a statement here. Okay, this should be useful. So to do a different set, you need to define these two expressions differently. So I executed those, I did not execute these, and execute this one. This is the total thickness H, which is equal to this in terms of the variables and T, which is ply thickness. Ply thickness will be given. Did I specify material yet? No. And then if I look at what A11 through A66 look like right now, after making these, this is what the A11 through A66 will look like. U's are constants, NN and Z and F are integer variables. And I'm ready to implement the poor man's implementation of branch and bound algorithm. Benjamin disappeared. I think dropped out. But usually his connection is finicky. Hopefully he'll come back. So I'm going to be solving this particular problem. And my E for this problem is given. U vector you can compute, and then T is given as 0.125 10 to the minus 3. And if I look at my, say, A11, you see that it's actually now only in terms of NF, NN, and NZ. Nothing else. Same as A22. Okay. And my objective function was trying to minimize or maximize A11. I forgot which one. Trying to maximize A11. And if I simplify this, my objective function is linear in terms of number of zeros, number of 45s, and number of 90s. My constraint says 12 minus A66 divided by 10 to the 6 must be less than equal to 0. And simplifying those G1 and G2. Those are my constraints, linear and linear. You have to check if they are linear before you submit. And then the total thickness, H1, is equal to 8. That's a linear constraint that says NF plus NN plus NZ, 2 times NF plus NN plus NZ must be 8. So all those constraints, I put them in a set constraints. So there are 3 constraints, 2 inequalities which are linear, this one and this one, and 1 equality, which is that. Now, I promoted the use of find maximum or find minimum, and this is the way to use it. And these will solve. But I also learned about that there's actually, what was it called? Linear optimization. This one. And I'm going to also try that. And you see, construction is a little different. So let me, this is a brand new, I just discovered it today. So I can either solve it using find minimum, or I can use it linear optimization. And you're gonna see actually there may be a difference between them. Yes. So let me type linear optimization here and type find minimum there. If I use find minimum, the constraint version of it is you put F and the constraints in one single list, and then put your variables along with its initial values, design variables, and their initial value. Or you can do this with only the design variables, X, Y, Z, etc., etc. If you go to linear optimization, then you can do F, constraints, and variables. So I'm going to do both. But I'm going to do find minimum first. And I'm going to copy this also. All right. I'm going to do these 2 lines first. And the reason for that is, in fact, I should probably do this one at a time. And I do the second one in this cell. It's find the minimum of this function at OBJ. Put the constraints in there in terms of the design variables, and came back and said, okay. And Z, number of zeros is 4.1651 layers. Number of 45s is 2.24226 number of layers. And N90 is minus. Okay? The general optimization assumes that the design variables can take any value between minus infinity and plus infinity. Now, to eliminate this undesired solution, I put an additional constraint that says number of 90s must be larger than 0. And and I execute that. And I get number of zeros is 3.51 and 2.24. This is continuous optimization, integer numbers. The number of 90s is actually 0. So we need to do branch and bound to find integer solution. Now, let me put poor man's implementation of branch and bound there, yes. Let me use linear optimization. I've never used this before. So let me see, how do I type F constraints and variables? And run it. Didn't run because there's a typo. Optimization. And it came back and said indeterminate. This does not seem to be working. It says the problem is unbounded. I'm curious. Let's check FOBJ is linear. Constraints. As an equality constraint. All right. So everything is correct. What I typed in, it's not finding the solution, and I'm gonna guess that there is a problem in this, that it's not working properly. I'm gonna report this to Wolfram. But I'm going to do one more thing. I'm going to put this constraint there as well. No. Basically what this file is supposed to do is add that constraint, and it must be greater than 0. Let's look at the optimization. It's possible that they restricted the input. So okay, they have to be greater than equal form. Yeah. So all of them have to be put in this particular form. This is fairly common in the algorithmic world, that they can solve the problem only if you call it properly, with the proper formulation. So equalities must be equal to 0. So you need to move 8 to the left-hand side, and all the constraints must be formulated in this particular form. So this will require additional work that we don't read that now. The constraints can be specified by, no, it actually says that you can do this. Huh. This is interesting. And the dual. Okay. I'm not going to bother you with these. So assume at this point that we really don't know anything about linear optimization. We're just going to use find minimum, which we did. Get rid of this. I'm going to get rid of this. Oh, am I over now again? You're not warning me. Just a little. Okay. Yes, my apologies. I ran over my time again. But I intend to complete this tutorial next time. I'm going to send it to you the way it is, if I didn't put it up there. And then we'll complete it next time around. So, sorry for going over. But these are interesting things that actually I'm assuming that we all are learning something new, including me. But this is how you make use of your software. You basically need to try different things. All right, gentlemen. Thank you for your time. And I'll talk to you guys Tuesday. If not on Monday, there's a help session on Monday. So please do come and ask questions during the help sessions. Again, to repeat the help sessions, I have one help session on, let me put up my calendar up there and so that you can see it. During those help sessions, I'm there. Mondays from 1 to 2 and Wednesdays from 1 to 2 and he said after 4 on Thursdays, right? Which is not there. Okay. See you either on Monday or Tuesday here.